Welcome to our presentation on modeling disease spread. My name is Luke Hall.
I'm Jasmine.
And I'm Jacob Manasco.
So for our introduction, to get everyone thinking about what we are going to be presenting on today, I would like you guys to think about a scenario where you got infected with COVID. And it's kind of, this part gets kind of silly, but like just say that there wasn't any precautions being taken. So there would be no masks, no 6 feet of distancing. Schools would still be open and everything would be basically as if there was like no pandemic at all. And then just think about like if you were at school, you were at Stan State, you were walking through a building and coming into contact with others. This could be stuff like as just bumping into them or walking past them, speaking with your friends or with your professors. And the question is like, how could we show this or model this mathematically? A key thing to know is that you obviously wouldn't be interacting with everyone at once. It's more like you speak to someone and then they go to speak to other people that they might know. And then as you might have probably already seen off the title slide and then the picture on the right, we are going to be approaching this scenario by using network science and using nodes to represent the interactions between people.
So I'm gonna start by going over some, hold up. I'm gonna start by going over some just simple terms that we need to know in order to progress on the presentation. And the first is gonna be network science. And network science is essentially study of networks, and a network is a graph essentially. More applied people tend to use the term network, while more mathematicians tend to use the term like graph. And then we're going to be using nodes. And whenever we say a node in this model, we're going to be talking about people. And you could think of like the nodes as the little silhouettes on the right, the little picture on the right. Each picture or silhouette represents one node or one person. And then notice how each person or node is connected to others. They're not all connected to the same ones, but they are connected to different nodes. And these are the degrees. The degree is the number of the connections between the nodes. And you could think of this as if, like, say I go to the grocery store and then afterwards I go to the gym and then I go home. I pass by all these different people, but those people are different than people that Jasmile passed by or Luke passed by. So the degree is unique for every node. And then let's go on to the SI model. We're going to be using the SI model for this presentation, where S is going to stand for the fraction of the susceptible people, and I is going to stand for the fraction of infected people. And both of these are fractions, so they're going to be less than or equal to 1. And if you add them together, you're going to get a whole. So we're going to be using this formula throughout the presentation in order to progress on our model. So then the next thing is the temporal over static. What static means is you're stuck in one time spot, while temporal means you're going through multiple time spots. You can think of this similar to what Jasmile said earlier. When think about you're in a hallway at Stanislaus State and you pass by different people at different times. That's like a temporal network. You pass by one person at this timestamp, then the next timestamp you pass by someone else, and so on and so forth. That's what we're going to be using through this model. And then we're going to be using mean field theory as well, specifically in my first model I'm going to discuss. And mean field theory is an approximation of a more complicated model. And we're going to be using approximations of the change of infected over time in order to progress. And then next is going to be the two graphs we're going to be using. So the first graph is a Bernoulli graph. And in this specific Bernoulli graph, each node has a similar number of connections per each time step. So there isn't no dramatic increase in nodes. While in Barbasi-Albert graphs, which is what we're going to be using for the third model, nodes in this one, nodes that have higher degrees or higher connections are going to be more favored to get more connections in the next timestamp, while nodes with lesser connections or lesser edges or degrees are going to have less connections. So you could think of a bunch of nodes over here with a bunch of connections. the next step, they're going to be way more. While ones down here don't have many connections, the next timestamp, there's still not going to be as many connections. And then next up.
So to just give a very brief and quick overview of what we are going to be discussing in the presentation, we are going to be going over 3 different models. The 3 models are going to be the mean field theory. The second one is going to be the multiple rounds of infection. And then the third one is going to be the degree-based mean field. I do want to just point out that we are going to be using differential equations in these models. So having some basic background knowledge regarding differential equations will make this presentation a lot more easier to understand. And then at the end, we will be going over the error testing done for the theories.
All right, so here's the first model. And we're going to be using the mean field theory model, which is a simple model that describes how an infection would theoretically spread throughout a network. And our goal here is to find the expected change of infected nodes. And we'd be doing that by using different edge combinations. And we have 3 edge combinations here, SI, SS, and II. And I'm going to be going over in a little bit of detail on the next slide what these mean. So notice in this one, this is what we are going to call an SS combination. Notice how there's no infected nodes here and 2 or 1 infected node. Let me restart real quick. So here we have no new nodes becoming infected. Notice how there's 2 susceptible nodes connected to each other. That's not going to result in 1 infected node being created. Same as the next image, where there's 2 infected nodes connected to each other. Notice there's still no new infected node being created. While in the final third image, we're showing an infected node infecting a susceptible node. This is resulting in 1 new node being created. And we're going to say that this SI or IS, either way, combination results in 1 more node becoming infected, where this proportion is the proportion of infected nodes is increasing at 1 over n. And that is where n is equal to the number of total nodes. Next. Once again, this SI combination is resulting in 1 more node becoming infected. And this is where the proportion of infected nodes increases at 1 over n. And we're going to be given 3 probabilities based off these edges, where SS is going to be given as 1 minus I, 1 minus I. And for the sake of keeping everything in terms of I, we're going to say that S is equal to 1 minus I. So once again, SS is going to be 1 minus I times 1 minus I. II is going to give us I squared. And SI is going to give us I times 1 minus I. And we're going to use those to create this piecewise function, which gives us the rate of change of the number of infected nodes, where 0 new nodes are becoming infected with probability 1 minus I squared, or SS, plus I squared. And then 1 new node is becoming infected with probability 2I times 1 minus I. And this 2 right here comes from, because notice how in the previous bullet, SI is going to give us I times 1 minus I. We're getting this special 2 right there because you could think of 2 nodes where 1 is susceptible and 1 is infected. It could be either one of these ones, this one or this one. So there's 2 possibilities it could be. So you got to take 2 times I times 1 minus I, and that'll give us this formula right here. And then we're going to be using this expected value formula. Xi times Pxi, which is going to give us the final formula that we need. So our probabilities, so how will we get this formula right here, the expected change of infected nodes? From the previous formula with the previous piecewise formula, let me slow myself down. You take 0 over n times its probability, and you're just going to get 0 right there. And then you take the 1 over n times its probability, which is how we get the formula down there, which happens to be d over dt is equal to 2n, or 2 over n times I times 1 minus I. And then there's one more step before we could finally plot this on a graph. And this is going to show us we need to take into account how many edges are actually activated. And you can think of an edge being activated as, say I'm at a party with a bunch of people. and then I start talking to Luke. That'll be one edge being activated. And then another edge is activated when, say, Jasmile talks to his friend. So those are two independent edges being activated. So for every independent action, that's a new edge. So you can think of that as being activated or being W. And then once we have these things, it's also important to note that in the specific model, edges that share a common node are ignored. And then finally, we could graph it onto a graph. And notice how on the left side, on the y-axis, there's the fraction of infected. And on the x-axis is some time over some time. And notice how over time, eventually every single person in the entire population becomes infected. You can also notice that there's two different graphs there. One is a blue one and one is a red one. The blue one is a bunch of simulations that were done, while the red one is actually our graph that was supposed to mimic the simulations. And look how accurate it actually is. It's actually extremely accurate. But now we're going to the next model.
Okay, so for our second model, it's called the multiple rounds of infection model. And this name might seem a little confusing just because in the model that Jacob just talked about, there could be multiple rounds technically if you made W equal to 2 or 3. So W being 2 or 3, meaning 2 or 3 connections. So there's multiple rounds of infection. But the key difference with this model here is that we're taking into account scenarios where there is an overlap of nodes connected by multiple edges. So for example, if you have node I right here, which is infected, and that connects to node J, which is susceptible, and then J goes and connects to node K, which is also susceptible, then you have an overlap in nodes. So you have J as a shared node between I and K. So now we have I infecting J, and then J becomes infected, and then J goes on to infect K. So we disregarded that in the first model. And so in this model, we're going to take into account both connections that don't do this, like 2 independent connections or 3 independent connections, but then we're also going to take into account scenarios like this where there is an overlap in nodes. So the process for finding the equations is similar to the first model in that we need to find the probability of each combination. But like I said in the last slide, this time we're including the overlapping nodes. So once we figure out the probability of each combination occurring, we need to figure out with that combination, how many new infections are there? So for example, if the combination, so we're going to group together all the combinations where there's going to be 1 new infection, and then we're going to multiply that by 1 over n using the expected value formula. And then for 2 over n, we're going to multiply that by the sum of all the probabilities where 2 new infections are occurring, and then the same thing for 3 over n. And when we do this, we end up getting these 3 equations where W is the number of connections. And so you can see when W equals 1, that's the exact same equation that Jacob derived in the previous slides. And then for 2 and 3, there's a little bit more complexity because we're adding in the probabilities where we have the overlapping nodes. So I am going to talk about the W equals 2 case. And just to clarify, that's when there are 2 edges activated. So to use Jacob's analogy of a party, if you have a party with 100 people in the room, in a big room, we're going to pick at random 2 connections. So 4 total people, or it could be 3 now that we have the overlapping node scenario, but you're looking at 2 different connections between nodes. So I'm going to go over all the possible combinations. First, looking at the combinations where we get 1 new infection. So here you have an infected connected to an infected. So there's not going to be any new infections there because they're already infected. And then you have this infected connecting to a susceptible. So that's going to be 1 new infection total. And with these, it's really important to pay attention to the edge combinations. So you have II, which is this first one that I talked about, and then IS, which is the second one. And the reason it's so important to pay attention to those is because there's going to be certain combinations that have the same edge combinations, but they're different in that one has an overlapping node and one doesn't. So you actually need to, in some cases, subtract one of the probabilities so you don't double count that combination. So I'll get to that in a second too. So the probability is underneath the two squares there. And it's basically just 2i squared. So that's representing the first connection here. We have I, that's the probability that I connects with an I, so I squared. And then multiply by 2s, so that's the probability of picking this s node here. And then the 1 over n being the number of total nodes in the entire population, is the probability that this S connects to this particular I. So 1 over n, 1 being the only thing that it can connect to because it has to be this shared one. And the reason we're multiplying 2 by both of these is because essentially the edges can be chosen in like 2 different ways. And this is another possible edge combination. And for this one, there's one new infection. You have an infected connecting to a susceptible, and then another infected connecting to that same susceptible. So the probability 2IS for the first one, and then for the second one, 2I, and then 1 over n being the probability that you, out of the entire population, you pick this individual as one susceptible that's already connected to the I. And just note the edge combinations here, IS, IS. So as I move into more possible connections for getting one new infection, you see here we have IIIS, which is the same as A, the same edge combinations as A. So that's why you see this subtraction here. We're actually subtracting the probability of A from this one, so we don't double count, because it's the same edge combinations, but it's a different scenario. There's no overlap in nodes. And then for D, same idea here. We have SSIS. And in this case, we're actually, so the 2s squared times 2is is just the simple probability of these two independent connections. So 2s squared because there's two s's here. And then 2is, an infected connected to a susceptible. But in this one, we're subtracting by a different probability that I haven't talked about yet. That's going to be in the upcoming slide. And that's going to be a combination where there's two new infections. So it's actually going to turn out that this, since we're subtracting A here, that's just going to cancel with this A, but I'll get to that in later slides. So then these are the possible connections where there's going to be two new infections. And so here we have 2, so S squared. So there's the susceptible connecting to a susceptible, and then 2I, and then 1 over n being that it links up with the shared node, similar to the last couple of slides. And then this one is ISIS. So that's actually one of the probabilities, if you remember, that we looked at in the previous slide. So we're subtracting that previous probability from this one because they have the same edge combinations. And then with this last one, we have ISIS, and notice these are the exact same edge combinations. So we don't even need to include this one because we just be subtracting it anyway, so we don't double count. And then, so to actually figure out the equation, we're using the same process that Jacob used, and that we're adding together all the probabilities. So in these previous ones, I labeled them with letters, and then they had the probabilities underneath them. So we're adding up all the probabilities of a combination where there's one new infection, and then we're going to end up multiplying that by 1 over n. And then the same thing, we're going to add 2 over n times the probability of the sum of all the combinations where there's going to be 2 new infections. So you get this huge equation here. And then once you simplify it, we plugged it into Mathematica and then factored out this common term. And so you get this equation here, which if we go back to this table, you can see that's the equation for W equals 2. And then when we pop this on a graph, so here we have 3 lines. So the blue line here, I guess you can't really see, but the blue line is the simulation, and then the red dotted line is the first model, the model that Jacob explained, the mean field with 1 round, and then the solid green is the 3 rounds model. So a 3-round model, and you can see that they're all basically together, so that there's not a lot of deviation here, and that just kind of leads us to believe that the number of rounds of infection doesn't really have that big of an effect on the rate of infection. So then that kind of led us to our next model, which Jasmail is going to talk about. And that's just, so the first 2 models, I just want to say, we considered all the nodes to be somewhat homogeneous. So like each edge combination is equally probable, so that they all had similar degrees. But with this next model, we're going to treat them differently. We're going to look at what happens when we separate the nodes and have some nodes with different degrees. So I'll let Jasmail talk about that.
So in this model, the degree of a node can basically be thought as like the amount of people that you would have in your social circle, since those are like mainly the people that you're going to be interacting with. Generally with this, we can say that people with large social groups are going to be connected to other people with large social groups. And then this is the same for people with smaller social groups. So people with small social groups are going to be connected with other people who also have small social groups. So in Barabasi-Albert graphs, the nodes that are connected have similar degrees, but they can vary drastically across the graph. This is what ends up making the Barabasi-Albert graphs different from the Bernoulli graphs. This is also why we are doing this 3rd model, because the previous 2 models only worked for Bernoulli graphs and not really for Barabasi-Albert graphs. In the previous models, it was assumed that each type of edge has an equal probability of existing in the graph, whereas for Barabasi-Albert graphs, the probability that an edge exists is further dependent on the degree of each node present in the edge, and that's because of the preferential attachment. So we just need to understand how the infection rate changes for each possible degree a node can have in the graph. And then in here, this is the system of equations. The lambda would be the average infection probability. Rho k of t represents the fraction of degree k nodes that are infected at a time t. And Vt is the overall probability that given an edge, it's attached to an infected node with degree k. And then here we want to understand the change in the number of infected degree k nodes, which would be pk. The way pk can change is if you have a susceptible degree k node with an edge that is susceptible to infected. The fraction of susceptible degree k nodes would be 1 minus pk, and k times w is counting what fraction of the degree of the k edges coming out of that susceptible node are of the form susceptible to infected. And then for our graph, the orange curve is going to be the mean field theory. The red curve is the degree-based mean field theory. And the dotted blue curve is going to be the median of the 10 simulations that were done. As you can see, the degree-based mean field theory graph matches much more closely to the blue curve's shape than the mean field theory. You can notice this a lot more in the time steps between 20 to 100. The red curve is steeper between these time steps, and that's basically what makes it match the simulation a lot better.
Okay, so for the error testing, we're going to use the root mean square error, which is this equation on the screen here. And the main idea here is you're doing predicted, which is you can think of as like our model minus the actual, so like the simulation. And then you're squaring it, dividing it by a constant, and then square rooting it. So intuitively, you can just think the closer the model is to the simulation, the smaller this number is going to be, predicted minus actual. So the closer the root mean square error is going to be to 0, which is good. So the closer we can get to 0 with the root mean square error, the more accurate our model is against the simulation. So we looked at three different things here. We're trying to, with the error testing, we're looking for our error to converge to 0 to see how we can improve our models. So the first thing we looked at is changing the number of simulations run. So on the graphs that all three of us have talked about so far, we ran simulations and then took the median and then plotted that on the graph and used that as our simulation line. So we're wondering, if we change the number of simulations run, will our model be a better fit for that simulation line? And it turns out, and basically you do this using this equation. So you take the difference in the fraction of infected between the model and the simulation, and then try and see if you get a convergence of the error. And with this, and in doing this, we didn't really see any convergence. So we basically concluded that the number of simulations doesn't have like a significant impact on the fit of our models. Then we turned to two other things that might have a fit, and then we can use to increase the accuracy of our models. And that was increasing the number of nodes. So in the simulation, if we increase the number of nodes, will our models match better, per se? So as you can see here, we have the root mean square error on the y-axis, and then the x-axis, we have the number of nodes increasing, or the number of nodes really meaning the number of people in our population. And so the root mean square error is way up here at 0.04, and that's at like about 150 nodes or 150 people. And then you can see as the number of people gets bigger and bigger in our simulations, that error converges towards 0. And then right around 1400 to 1500 at the very tail end, you see the error is pretty much flatlined at 0. So just looking at this, you can tell that increasing the number of nodes does allow for our models to match better with the simulations. So that was just something, if we're ever going to do this type of testing again, we can increase the number of nodes and see what happens there. And then also, we did a root mean square error test with the first model, the model that Jacob presented, the mean field, and then the model 3, which was the degree based, the model that Jasmine presented. And here we're going to graph both of those on a Barbasi-Albert graph and then look at the root mean square errors. So as you can see, and this was just we were trying to get some like quantitative evidence that the degree based is a better match for the Barbasi-Albert graphs. We kind of already knew it, like it makes sense. But this was just to get some actual evidence here. So on this graph, the purple line is the mean field model, and then the blue line is the degree base. So you can see at every point, and it's the same, we're graphing this against as we increase the number of nodes. And you can see at every single point in this graph, the root mean square error for the degree based is well under the root mean square error for the mean field. So this basically just tells us that if we're going to do a degree based model, we're definitely going to want to use a Barbasi-Albert graph versus a Bernoulli graph.
So to start the conclusion, we realized that most of the models that we discussed throughout all three of the models were actually very accurate. They actually matched very well with all the simulations that we ran. Now, although we learned some things such that different graphs are better than others. For example, the third graph we used Barbasi-Albert, and that matched well, but the mean field theory model didn't match as well with the simulation. But in the end, all three of the models actually matched extremely well with the simulations.
And then just something to note, all the graphs eventually plateaued at 1, and 1 being 100% of the population becoming infected. So that a translation of that is without control, everyone becomes infected eventually. So that's just like some kind of interesting with like the pandemic that's going on right now. If at least with these simulations, if everyone just acted normally, then our models suggest that every single person in the population will get infected at some point. And then, so takeaways from error testing, essentially, the takeaways from that were the number of simulations run, it doesn't really matter in terms of getting that root mean square error to converge towards 0. But what did matter was increasing the number of nodes. So, and that does make sense. Like the more people you have participating in the simulation, the more likely or the better the fit for the model, because the more accurate it's going to be if there's more people participating. And then also, like Jacob said, the graphs do matter too. So all the models, like just taking into consideration what graph you're going to use for that, we figured out that there's a difference there too. So.
So for our future research, we can do the multiple round model with Barbasi-Albert graphs, and that just basically means doing the second model that Luke presented with using Barbasi-Albert graphs instead of using the Bernoulli graphs. And then we can also try doing the SIS or the SIR model. For the SIS model, someone would be susceptible, and then then they would get infected for 14 days, and then they would go back to being susceptible again. So that means they're still like included in the model because they're still able to get infected. And for the SIR model, when someone is susceptible and then they go to infected, after 14 days, they would eventually become recovered. And that means that they would either have antibodies or they would have died from the infection, and then that they wouldn't be included in the model. So they just don't keep going back to being susceptible and then getting infected.
And that's it. Thanks for watching. Hope you enjoyed.
Thank you.